Hello, so in today's class, we'll see a problem of distributing distinct objects into identical boxes. Okay. So this gives rise to what is called the Stirling's number of second kind. So we are going to look at the Stirling's number of second kind. So let us define what is called the Stirling's number of second kind. So here you will be distributing distinct objects into identical boxes. So given non-negative integers r and n, the Stirling's number of the second kind denoted by capital S of Rn. So first kind is denoted by small s of Rn, and the Stirling's number of second kind is denoted by the capital S of Rn. So that is defined as the number of ways of distributing are distinct objects into n identical boxes such that no box is empty. So the Stirling's number S of Rn is defined as a number of ways of distributing r distinct objects into n identical objects such that no box must be empty. So we will look at a few obvious results of the Stirling's number. Okay, so S of 0, 0 is defined to be equal to 1. That if number of boxes and number of object is the same. നമുക്ക് 0 box 0 object ആണെങ്കിൽ the distribution can occur only in single way. So S of 0, 0 is defined to be 0, and S of R0. So this is a number of ways of distributing R objects to 0 boxes. So there are no such way of distributing, and again number of ways of distributing 0 objects to n boxes. So such distribution is 0. So S of R0 and S of 0n are 0 for all Rn belongs to n, and again S of Rn is greater than 0 if r greater than or equal to n greater than or equal to 1. So whenever the number of objects is greater than the number of boxes, you can keep at least one object there. So therefore there will be the number of ways of distributing the objects. So S of Rn will be greater than 0 if r greater than or equal to n greater than or equal to 1, and again S of Rn will be equal to 0 if you have n greater than r greater than or equal to 1. So if n is greater than r, if the number of boxes are greater than the number of objects, then there will be obviously an empty box, so which is not possible because none of the boxes must be empty. S of Rn will be equal to 0 if n greater than r greater than or equal to 1, And again the next result is, so if you take S of R1, so this is the number of ways of distributing R objects to a single box, so that can be done only in a single way, so where R is greater than or equal to 1. And S of R, so this is the number of ways of distributing R objects to R boxes, so that can also be done only in other object or box like the boxes are identical, so there is only one such way. So this is for R greater than or equal to 1. So we have S of R equal to 1. Again, few more properties are, so we will see the proof for these properties. So we will see it at the end. So S of R2 is equal to 2 raised to R minus 1 minus 1, and again S of R3 will be equal to 1 by 2, 3 raised to R minus 1 plus 1 minus 2 raised to R minus 1, and S of R minus 1 is given by RC2, and S of R minus 2 will be equal to RC3 plus 3 RC4. We will see the proof for this. Okay, we will see it towards the end. So before that, we will show a recurrence relation. Appo nammal Stirling's number of first kind in a number recurrence relation kandu. Similarly, for Stirling's number of second kind, you have a recurrence relation which will help us in finding the Stirling's number. So we have got all these results. So using the results and the recurrence relation, we can find different Stirling's numbers. So we will move on to the recurrence relation. So the relation is, so let us write as a problem. So show that S of Rn, capital S of Rn is equal to S of R minus 1, N minus 1 plus N S of R minus 1, N, where we have R and N belongs to a set of natural numbers with, so R must be greater than or equal to N. So we need to show that S of Rn is equal to S of R minus 1, N minus 1 plus N S of R minus 1, N. So S of Rn is a number of ways of distributing R distinct object to N identical boxes. So we are having R, R distinct objects are now so let us see the proof for this. So what we do in the proof is, so you are having R distinct objects. So when you have R distinct objects, so take A1 to be a particular object. In distribute there can be two cases. So the first case is A1 is the only object in a box, and A1 comes along with other object. So there are different ways of distributing R objects to N boxes. All distributions but there can be distributions where you have A1 as an only object in a box, and there can be distributions where A1 is mixed with the others in a box. So we will look at what are the number of ways in which A1 occurs as the only object and A1 occurs with the other objects. Okay. So when you add up these two possible cases, those are the only two possible cases with respect to A1. So number of ways in sum S of R and so using that we will show the recurrence relation. So let A1 be a particular object of the R distinct objects so in any way of distributing R objects into n identical boxes such that no box is empty. So either A1 is the only object. So let us take it as say case 1. So A1 is the only object in a box, or the second case is A1 is mixed with others in a box. Now let us look at what happens in case 1. So in case 1, so A1 is the only object in a box. So A1 ne namukku distribute cheyinde A1 oru box like povum. Baaki namukku R minus 1 objects aanullathu. So R minus 1 objects has to be distributed to n minus 1 boxes. So the number of ways of distribution will be S of R minus 1 n minus 1. So in case 1, the number of ways of distributing is S of R minus 1 n minus 1. കാരണം A1 already ഒരു ബോക്സിൽ ഒറ്റയ്ക്കാണ്. ബാക്കി നമുക്ക് R minus 1 objects ഉണ്ട്. അതിനെ n minus 1 ബോക്സിലേക്ക് ഡിസ്ട്രിബ്യൂട്ട് ചെയ്യണം. That can be done with S of R minus 1 n minus 1 ways. Now in case 2, first let us put the R minus 1 objects to the n boxes. Okay, so the R minus 1 objects are distributed to n boxes, and this can be done in S of R minus 1 n ways. ഇനി നമുക്ക് A1 എന്ന് പറയുന്ന ഒബ്ജക്റ്റ് ബോക്സിലേക്ക് പ്ലേസ് ചെയ്യണം. Now A1 can be distributed in n ways. So A1 can either go to box 1, box 2, or etc. box n. So A1 can be put in any of the boxes in n ways. So therefore the number of ways in which case 2 can be done, that will be n into S of R minus 1 n. So therefore by addition principle, so S of Rn will be equal to S of R minus 1 n minus 1 plus n S of R minus 1 n. So this is the number of ways of distributing R objects to n boxes. So this is the recurrence relation which gives the Stirling's number of with given R and